Okay, on that note, shall we get underway? See if we can run through about 10 chapters in about it won't be 3 hours. I like to call it what is it? They always ended the classes at 10 to 9. 2 hours and 45 minutes. Let's shoot for that. Okay. So back in your chapter 1, book 1, near the beginning, there's a glossary. So please remember that you should read glossaries. You should be familiar with the jargon and the definitions as it applies to power engineering. Some of the terms that you will read there, you may tend to want to think, oh, I know what that is. I'm not going to read what it is. That might surprise you because some of the terms in the glossaries pertaining to power engineering are not going to be the same definition as you might have learned in some other industry. Okie dokie. So baffles and drums and mud drums. If you have a drum on a boiler, keep the terminology clear. If it's a water tube boiler, it's going to have a drum. If it's a fire tube boiler, we're going to call it a shell. That's going to help keep those boiler types straight, right? So Bob, you have a hand up. Is there a question or?
Yes. Did you want to record this review or not?
I do not normally record the reviews. It's a PowerPoint that's there in week 5 for you.
Okay.
Certainly, I want you to review it, and it's to have me read it to you again. I think it's better just to go through it yourself. So, okay, yeah. Thanks for the reminder because sometimes I do, but usually I don't. I've had a really good attendance record. Most every student has attended every class. So if I have people that are working away or working every other week, then we can do a compromise on the recordings. So there's things like forced draft fan, there's headers, there's heating surface. I'm going to review all the important ones here. Heating surface is a really important one. Job 1 for power engineering is transfer heat. And we are 9 times out of 10 transferring heat from some medium to another, a water side or a fluid side and a gas side or a fire side. And in every case, there's a heating surface. So the concept of what comprises a heating surface in a boiler in particular is a very important one. Let's get my highlighter going. So heating surfaces, very important concept. Parts that have water or fluid on one side and combustion gas or some other temperature of water or fluid on the other side. Okay, we use heating surfaces, transfer heat. Generally, it's some kind of it's clear that it's some kind of a heat exchanger. We don't look at those and talk about those till later chapters, but in boilers, it's that interface between the hot gas and the water that we're heating. A stack or a flue or a chimney, some way to remove combustion gases, generally to make things hot. In power engineering, we're going to burn some fuel. There will be hot gases, and they need to be dealt with or handled. Superheaters, if we do have opportunity to heat steam higher than what's called saturation temperature, that will be done with something called a superheater that we do not discuss at great length in this course. But we will talk about things like an uptake, which is a duct, between a boiler furnace and supplies those gases from a furnace into the stack, depending on the design and the type of the boiler. Okay, water tubes, we'll have a closer look at water tubes, and we'll have a closer look at all of the definitions in the glossary. A baffle is a barrier or a panel. So this is a boiler with water in the tubes, gas being created by a fire over here. It's very likely a coal burning boiler. Neat thing about older coal burning boilers, they were easily converted to natural gas fuel. Just put a burner in place of where you used to burn the coal, and you can have hot gases heating up your water to make steam. So these guys here are baffles. And this one over here is a baffle. So now when the gases enter the area with the water tubes, they have to travel over and down around the bottom of the other baffle, and then we have a how many pass boiler. Three times our hot gases pass around the tubes. Okay, drum. So we have pictures of drums. The drum looks like this, and tubes are on the outside, connected to go to a lower drum. This is a water tube boiler. From the inside, it looks something like this. All of these tubes are connected around here. Steam drum is a standard feature of a water tube boiler. Remember, a fire tube boiler, we're going to call it a shell. It kind of looks like the same thing, but all these tubes are inside, okay, underneath the water with hot gas. So eventually you're going to keep those two straight, okay? Steam drum up here on the top, because the steam bubbles in the heated water are going to go up. And somewhere in this drum at the top, we're going to do what's called separate the bubbles and the water. The water will sit on the bottom. All these tubes are full of water, and then at the bottom we have a mud drum or a couple of mud drums. Okay. So this one's called an A type. I like that one. It really does draw an A, right? Two mud drums at the bottom, one steam drum at the top. Over on the right here, we have a package boiler on a truck. And it's steam drum at the top, mud drum at the bottom. Bent tube style, so there's water walls surrounding this furnace. And there's the burner, and the furnace is inside. So try to keep it clear. Drums for water tube boilers as opposed to a shell. All these tubes inside the water, underneath the water level, those are fire tubes. Okay, these are fire tube boilers, and this is a fire tube boiler. So we're going to call it a shell. We're not going to call it a drum. Sort of the same function, but we're just going to use that memory key to keep those two concepts straight in our mind. What is a header? It's a large pipe that collects other pipes. It can be varying sizes like this, or multiple smaller pipes connected to a larger one. And it's often called a manifold, header or manifold, just a way to connect several pipes together. Heating surface, reminder, all the parts, pipes and tubes, water or steam on one side, and the fire or hot combustion gas on the other side. So this is a water tube boiler. Water's in the tubes, and hot gas is surrounding the tubes. Okay, we have our steam drum at the top. If there was, on this particular style, if there was a mud drum, it would be a little guy over here on one side that would run perpendicular to the drum at the top. It wouldn't look like your classic steam drum at the top, mud drum at the bottom. That looks like this. All right. So heating surface, very important concept. Back in the day, they had kettle style boilers, a big old steel tank full of water. And so water is in here. This is the drum of the kettle type boiler. And hot gas is over here. This is some kind of a solid fuel. Heating surfaces have water on one side, so the water is inside. And the hot gases are here. So the heating surface is all the areas where the hot gas is exposed to that, heating up that water. So let's draw a heating surface. Okay. A stack, this is a duct or tube or chimney or flue. Sometimes called flue. Classically, we see the big old stack. We know what that is. It's a chimney. Modern plants with a number of small boilers. This can be the ducting here, but it's the same thing. It's taking the hot gases away. So this is multiple boilers here. 1, 2, 3, 4, 5, 6 times 2. There's 24 small boilers here. They're all connected together to a common flue or duct. Water tube boilers, steam drum on top, mud drum on the bottom. Furnace is where the fuel is burned. So somewhere in here, we're going to have burners. Yeah. Burn a bunch of fuel, burn a bunch of gas, burn oil, different things. Heating up the water in the water walls. All right. Boilers that have drums connected by water-filled tubes are classified as water tube boilers. Combustion gases travel over the outside surfaces of the tubes and transfer their heat to the water. Okay. Some specific boilers that come under the water tube, as chapter 1 is water tube boilers. This is from page number 1-3, called serpentine tube water tube boilers. So these copper water tubes are bent in an S fashion. And inside the heat exchanger area with a burner below, and hot gases and flames are coming up through around the tubes and out the flue. Combustion chamber is located below the tubes. And if you examine this drawing very closely, or a boiler that looks like this, there's no fans. This is a natural draft furnace. Packaged tubular steam boilers, similar to this, but one continuous loop of tubing around and around and around and around and around and around and around, and then a combustion chamber in the bottom. And around this, what's called an outfired burner here, they've got some steel sheathing to protect against the erosive action of the flame. So naked flames impinging on tubes in any boiler is not a good situation. So we have these are small little coils wrapped around a burner, very close proximity. So we have some extra protection in there. It's hard to keep the flames from impinging on that, sometimes copper tubing. Circulation in a longitudinal drum boiler. So this kind of a boiler has some long tubes underneath an upper steam drum. And we have some hot gas coming in here. It doesn't matter what kind of fuel, how many passes in this boiler.
Three
times, yeah.
Hey, is there a special name for the water tube that comes down to feed the diagonal tubes?
Yes.
Okay. That's right. Thank you.
I think this one's right. I think this one's right out of your book. If this isn't the one right out of your book, this is I think out of the older book. The one in my book 3.2, 3.5. My book is 3.5. Is pretty much the same diagram. It's busier with more detail, but it's also called a downcomer. And then the other side of it that you can't see in this one is a riser. So if you point an arrow down, water's coming to the down. And this is a great segue into the next thing I want you to remember. You might see this exact drawing again. And you're going to want to remember the points on the next slide here. Water enters the lower part of the longitudinal steam drum. Number 2, it flows through the downcomers to the lower header, heated as it passes through the boiler tubes. Because we have hot gases heating these tubes, the heated water starts to bubble and boil because it's expanding into steam. And as it expands, it becomes less dense. So the more dense water wants to be at the bottom, coming down the downcomer, and the less dense water is going to go up a riser back into the drum. This is the feed water entry here. It's supposed to be labeled. This internal pipe is where the feed water is entering. The level in this drum would be approximately here. And circulation will go in a clockwise direction. Okay, that's why these tubes are tipped up at one end. The less dense bubbles and steam are going to rise, and that's going to start that circulation across the drum. And you need to relate this description of circulation to this drawing. Okay. A-type, 1 steam drum, 2 mud drums. O-type, 1 steam drum, 1 mud drum. Or a D-type, which is much similar, just furnace is kind of off to one side. Instead of the furnace in the middle, it's off to one side. So these are all bent tube boilers. On the right side, we have 2 drum bent tube boilers. This is a 3 drum bent tube boiler. So which type is this one?
O-type.
Yeah, just like on the sign here. Okay, that's this one. Sometimes they're tall and skinny like this. Sometimes they come out farther on the side, but if they're symmetrical, we're going to call it an O-type. Kind of looks like a circle. Water walls formed by tubing and steel plate membranes arranged around the furnace. This is so the water in the water walls can absorb radiant heat. Bent tube boiler design allows the tubes to be attached radially on the outside of the drum. Okay, so these tubes are attached in a radial direction. And what's important is these are membrane type water walls. So These little strips of metal between the tubes are welded between the tubes. The description of a membrane type water wall is not metal sheathing on the tubes or covering the tubes. The membrane water wall looks like this on the boiler in the wild. It may have outer steel lagging or covering on the outside of insulation. This is the membrane water wall here. The tubes are joined by these metal strips in between. Okay. A little review of chapter 1, a quickie for chapter 1. Salt minerals concentration below safe limits on a packaged tubular steam. Whether we do some automatic blowdown. So we've talked a bit about blowdown. We'll talk about it more, but what that does is help us keep the dissolved minerals down to desired levels. Packaged tubular steam water, whether water wall tubes are protected with a steel sheath. So this is packaged tubular steam boiler. So make sure you're clear that that is talking about this guy. Okay, it's got this metal ring to keep the flames contained at the bottom of the boiler. All right. To prevent against the erosive action of the flame. Longitudinal drum boiler feed water, where does it enter the drum? I talked about the 4 directions of feed water circulation. The lower part of the steam drum. Let's go back to that drawing because
It's the downcomer.
well, the water is entering here. So this is the lower part of the steam drum. Okay, and the one in the book has that feed water inlet over on this side too. Okay. In the first time we went through this chapter, there's some boilers with it on the left side and the right side. What you want to remember, it's in the lower part of the drum. Okay, this is the feed water. Right? Not in the top. Students usually pick the top. But you guys are going to remember it's in the bottom part. Right? Lower part of the longitudinal steam drum. None of these. Furnace enclosure. A vent tube boiler has a furnace enclosure. The walls of the furnace made up by something called water walls. They're not called steam walls, header walls, heating walls, or tubular walls. They are water walls. Might be called membrane type. Might be called membrane water walls. Okay, they have metal connecting the tube. Certainly there might be metal cladding or covering on the wall outside of insulation, but the metal is connecting the tubes. Vent tube boiler design, the furnace is lined with these membrane water walls because it gives us greater exposure to the radiant heat. Okay. Not convection, not conducted, not latent heat, not residual heat. We're getting greater radiant heat transfer. Vent tube boilers, advantages, all of the above. Better heat transfer. Boilers can be built with less refractory. Refractory is heavy. Refractory cracks and breaks down. And when we use bent tubes like this, we can make all kinds of shapes and arrangements of tubes and boilers. So less limitation on the design. So all of the above. Advantages a bit Vent tube boilers, better heat transfer, radiant heat absorbed by the water walls, better use of space, reduction in materials, mostly because of less refractory. E-type vent tubes running from single upper drum to two lower mud drums. D-type, one steam drum, one mud drum, and a furnace over to one side, shaped like a D. Sometimes it's over on this side. It's still a D-type. Walk around the other end and it's the right way around. O-type boiler, when it's symmetrical, they call it an O-type. O-type has two drums. A-type has three. Water tube boiler. Even these kind of boilers can have multiple passes. So we have a burner here, hot gas is going down. There would be a baffle up the middle here, and then hot gases will come around this way. So this is a two-pass vent tube water tube boiler. Okay, one pass this way, one pass back. Package boilers, they're easy to install because they come assembled. They've already been run and tested and inspected from one supplier. All the fittings and equipment and warranties and similar things. Problem with your boiler, call the manufacturer. Any questions on chapter 1? I'm just noting down the time here for chapter. Okay, cast iron sectional and modular boilers. Cast iron sectional boiler. These are for generally heating systems, smaller and medium-sized buildings. These are not big, high-pressure boilers. These are not usually power boilers. Heating boilers used for heating that are above a certain pressure can be considered power boilers, but they're not being used to generate power. They're being used for heating. Because they're at a certain pressure, they're going to be considered power boilers. That just means they're governed by a different section of the code. And we'll touch on that a little bit and look at the greater detail about the codes in book 3. Boilers are built up, meaning we have sections and we can stack them like pancakes, or we can stand them up on end like toast in a toaster. So this is a vertical flow cast iron boiler. This is a horizontal flow caster. So these are stacked, or sections stacked, and these are vertical. Can be vertical or horizontal. Depends on the brand, depends on the style. Sections are connected with push nipples, and tie rods hold the sections together. So vertical, they're standing up. There's sections in here, 1, 2, 3, 4, 5, at least 6, if not 7 or 8. And this one, the sections are lying down on top of each other. Push nipples are the way the flow goes from one section to another. Push nipples are here and here. This one has push nipples over here. Let's do this. So push nipples are here, and here, and here, and here, and here. And the whole thing is held together with tie bolts or tie rods. Okay. Various shapes and sizes, all these are stacked together. Is this vertical or horizontal?
Vertical.
Vertical is this way. And when they're stacked up like pancakes, that's horizontal. Okay, it lines up with the horizon. Here's a push nipple port. This is where we connect the flow between the sections. Some of these sections are formed around a furnace like this. This is called a water leg arrangement. A variation on that is called a wet bottom. So that if this was connected across, it's got a wet bottom. That's one like this with a wet bottom. It's just about more heating surface. So this much heating surface around a flame or a furnace is 25% less than if you have it completely surrounded, right? So, David, what's going on? You're getting kicked out, or?
Yeah, I'm just having some internet problems right now, but fixing it.
You're following most of this? Gonna figure it out?
Yeah, I got it.
Okay. So connected at the bottom is called wet bottom. Wet bottom cast iron sectional boiler. And here's our tie rods. So the connection for the water to flow is push nipples. And the thing that holds the sections together, bolts between section to the next section. Sometimes these bolts just go from one end all the way to the other end, and long bolts tie the whole thing together. Still tie rods. So vertical or horizontal?
Horizontal.
Yeah, they're stacked up. So here's the push nipples. This furnace, atmospheric furnace, is down below, as it usually is. Hot gases are created down below, and then hot gases go up through the top, heating up all the sections. And here's the flow. Here's the flow there. We have the atmospheric burner at the bottom. This one on the right shows the hot gases going up to the stack, and the water flow is through the push nipples between the sections. So cold water coming in here, hot water coming out here, hot gases coming out the top. What's good about cast iron boilers? They are made of cast iron, which is considered to be high resistant to corrosion. These are small pieces. The boiler can be taken apart into 4 or 5 heavy parts, moved around, brought in through a man door. Ease of assembly, sections will fit through a standard doorway. The whole boiler might not fit through your doorway. Take it apart, carry it in, put it back together. So choice of assembly location, easy to replace. The old boiler is done. You can take it apart, take it out, take it away, and bring in a new one. If you want a bigger boiler, the next time you put it back together, add some more sections. The courses really stress this at all levels. Is it easily practically done? Often I don't think so much, but the theory is the ability is there. So they call it an advantage of cast iron boiler. So there's a picture of a sort of an interesting shaped cast iron boiler, but you can see the vertical sections 1, 2, 3, 4, 5. And you can see that the water surrounds the furnace to increase the amount of heat transfer, the surface area. All of the above advantages of cast iron: high resistance corrosion, easy to assemble, choice of where you assemble it, easy boiler replacement, and enlarging by adding a section. Heating boilers operate most efficiently at continuous full load. This is a random question, but it'll come back in the appropriate chapter. Cast iron boiler sections are connected with
Push nipples.
push nipples. Thank you very much. Held together by.
Tie rods.
Thank you very much. Water lakes, what do they do?
Increasing the heating surface.
Yes, correct. This is more. How do we increase it more? We have a wet bottom and we add 25% more. There's the wet bottom. More the better. Downside of cast iron is cheap, it's corrosion resistant, but it's brittle. So we can't make big high pressure boilers. Choice of assembly location, they are not lightweight. They are not for high pressure. They're not big boilers, so not large capacity. And being brittle is not an advantage. If we put some cast iron boilers together in modular boilers and connect them up for water flow, what's memorable about water flow in a modular cast iron boiler according to page 2-12? Continuous through all the modules. So we run the water flow, the circulating pumps, water is going through our system all the time. One boiler may start up 2 or 3 or 4 in that modular setup, 2-12, but remember that the water flow is continuous. Multiple boiler installations have separate circulating pumps and use something called a step controller for operation or control. And that's the diagram from the book that talks about modular setup. So we've got horizontal cast iron boilers and a number of them connected together, and water flow is continuous. Supply here and return here. Okay. Any questions on cast iron boilers?
What is the step controller?
Step controller,
Yes, please.
what does it do? Please refer to page number 211. Boilers are operated in sequence. So when you have this kind of a setup, you're going to have a thermostat. We want to have 70 degrees. Step controller will start up one burner, one of the modular boilers, and it may say, holy cow, we're only 60 degrees, let's fire up all 4. And then if we get up to 69, it's not going to shut them all off, it's going to shut one off, shut another one off in steps. Okay, that's why it's called a step controller. And that's a very, very basic, simple explanation. It's way more complicated how it does that, but it just steps the capacity up to where it's needed and then steps it back. All right. A little change gear conversation, water tube, fire tube. So 2 important types of boilers, often tricky to keep straight. Is it a heating boiler, power boiler? One of these chapters, we're going to take a little very shallow look at the difference, show you where to find the difference. Blow off and blow down. similar things, but can be very different. Open a valve to start the flow, close a valve to stop the flow, as opposed to a switch, close a switch to start the flow of electrons, or open a switch to stop the flow of electrons, okay? Fire tube boilers, so different arrangement than what we were looking at up till now. Fire is in the tube. And we're going to call this a shell because we don't have a bunch of tubes making water walls on the outside. The tubes are all inside the boiler, or inside the shell, surrounded by water. Hot gas in the tube, water surrounding the tube. So there's a cutaway view of a basic fire tube boiler. This one we call it, this is a very common fire tube boiler used in industry and oil field and portable boilers, packaged boilers. Most packaged boilers are this kind of a boiler. It's called a modified Scotch type boiler, and we'll touch a little bit on what that means. Okay, here's our little brief introduction to codes. So in chapter 3 on page 4, right here, 3-4, it talks about, let's do it this way. Yeah. Let's start here actually. So there's a whole bunch of ASME codes. I don't even know how many. They add a couple sections every now and then. They govern all kinds of things, piping and power plants and boilers and blah, blah, blah. Only 4 you need to even think about, even in your 4th class. So remember these numbers, 1, 4, 6, and 7. What really mucks a lot of students up, and it's trapped me, is they use Roman numerals. So they have 1, 4, 6, and 7. I suggest if you're going to have some code questions in your exam, which will happen in book 3, is you kind of train your brain to start with number 1 is at the top. And if you write these numbers, 1, 4, 6, and 7, 1, 4, 6, and 7. Remember that we construct a boiler first. So construction is at the top. Twice, 1 and 4, construction. Okay. If anything is asked about that hasn't got something to do with building the boiler or construction, comes under care and operation. Okay, so then we just have to remember power, heating, and power. ASME number 1 is power boilers, construction. 4 is heating boilers, construction. 6 is heating boilers, care and operation. Anything that's not building it is care and operation. And number 7 is power boilers. All the codes questions, except for all the possible codes questions in this entire course, all the way, starts in book 3 and goes to the final exam. You can see the answer right here. So if you know the title of these 4 codes, 6 and 7 is care and operation of heating for 6, power for 7. If you start your scrap paper come exam day with 1, 4, 6, and 7, construction, care and operation, power, heating, power, you can answer all the code questions. You don't need the books. The books will cost you a pile of money. If you are going to 4th class, certainly buy the expensive books, as many as you can get your hands on. We don't even recommend buying the B51 and B52 anymore, because that's another $900 on top of all your expenses. So I can show you how to make the code questions fairly straightforward. And just to kind of warm you up for that, we're not going to study it or answer questions on it until book 3. But it's in this chapter 3-4, the difference between power boilers and heating boilers. So as long as we're below 15 psi, it's a heating boiler, section 4. If we go above 15 psi or 103 kPa, it's a power boiler, and that's section 1. Okay, and then there's some things here about hot water heaters and tanks. Remember this number. Hot water heaters cannot run over 99 degrees. Heating boiler cannot run over 121 C. Some code books will say 120. Okay. So construction, 1 and 4, power and heating, care and operation, 6 and 7. And it's really important to write down 1 and 4 and 6 and 7. For myself, these two, I just have always mixed them up. I've always looked at IV and think 6, write down 6 and VI. If you write down 1, 4, 6, and 7, you can't mix them up. Fire tube boiler designs are based on the water in the shell surrounds the tubes. The hot gas passes through the tube. And there's your fire tube boiler. Make some fire. The fire will go through tubes to your stack. It's inside the shell. The water gets boiled and steam comes out. Steam and hot gases. Horizontal fire tube boilers, the water in the shell surrounds the tubes, heat from the hot gas passes through the tube walls into the water. So this is fire tubes, this is this chapter, this is water tubes, that was the last chapter. Textbook goes into quite a bit of history of different kinds of boilers. We're just going to really lightly look at a couple of them. 3-5 describes HRT. HRT means horizontal return tubular boiler. This was an early form of fire tube boiler. Okay, so this one has a fire. Early boilers, we didn't have natural gas, we had coal and wood. So the fire's underneath the boiler, there's some tubes heated up by the hot gases, and then another second pass out the stack. All right. Horizontal return tubular boiler was one of the earliest forms of fire tube boilers. So pretty much like this. This would be an older design and then a newer design like this. Water tube is not fire tube. Remember, there's a difference. 3-6 shows and talks a little bit about locomotive boilers. We wanted to move things around, and we needed some extremely powerful engines. We put some boilers on wheels, and we can drag hundreds and hundreds of thousands of tons of cargo around by having a boiler on a train. Of course, we've gone way past that now, right? Any of you ever been out to Gibbons, Alberta Railway Museum? They've got some of these old steamers out there. Before COVID, you could go out there on weekends, and some of my retired buddies from Redwater Fertilizer Plant have got amassed a collection of steam locomotives, and they're on tracks, and you can drive them back and forth out there. It's kind of cool. Firebox boilers. So a variation on a theme. We've got a firebox. We've got some fire tubes carrying gases down inside of a shell. Hot gases come back another way into a smoke box out the stack. So firebox boiler is a 2-pass boiler. We started to design horizontal return boilers, redesign and improve for efficiency, make them even lighter, and then they became Scotch marine boilers. Scotch for Scotland. Some people from Scotland made these designs, and now we could have steam engines on ships. Okay. Scotch marine boiler. What is a wetback? So we have a burner here, creating hot gases. It goes to the end of the boiler. The back of the boiler is surrounded by water. Okay. So the back of the boiler is full of water. We call it a wetback. And then a second pass of tubes. So we have one pass here. Smaller tubes are the second pass. Steam space in the top of the shell. So the Scotch boiler was the forerunner of this old guy with the wetback was the forerunner of the modern fire tube boilers that we see all over the place. Okay. These guys are called modified Scotch boilers. And that's the definition of a package boiler. Okay. Some other sort of unique boilers that come in this chapter, come under the fire tube boiler chapter, vertical tubeless boilers. So there's a vertical fire tube boiler on 3-10. These ones are from 3-12. Vertical tubeless boilers. Small capacity vertical fire tube boilers. Generally, these are just hot water heating boilers. They have two sections, heat exchangers above and combustion chamber down below. Vertical, that's steel plate heating boilers. And then another vertical tubeless boiler on page 313. Firing occurs in the central pipe, vertical tubeless boiler, furnace chamber, combustion gases. So we've got water surrounding a tall, long burner that this one's fired from the top down. Okay, so power boiler, section 1, anything above 103 kPa. Below 103, heating boiler. Not enough pressure to make any power. Gases travel through boiler tubes, which are surrounded by boiler water. This is a fire tube boiler. Not necessarily packaged. We don't call it a tubular boiler. We call it a fire tube boiler. It's definitely not a water tube boiler. And it's not a coil type boiler. HRT was the early or original fire tube boiler. HRT again. Steel plate vertical fire tube unit with 2 sections. If it's on top, it's the heat exchanger. Usually the flames are allowing heat to rise. The one we saw there with the down-fired burner from page 313, also the ones on 312, they have, if you look at the diagrams in the book, you'll see there's blowers. So with a blower, we have the ability to have the heat exchanger below the burner or the furnace. Steel plate vertical fire tube with 2 sections. The upper part is heat. If a boiler comes completely equipped, mounted on a base, what are we going to call it? It might be a power boiler. It might be a heating boiler. I don't know what a condensing boiler is, but it's not necessarily a heating or power. It's a packaged fire tube boiler. Okay, not cast iron. This one. Packaged boilers, factory built, supplied, equipped, and mounted on their own base. So if you're not sure, you have a closer look and you see a skid or a couple of beams that kind of tie the whole thing together. Even the gas train is on there. It's probably a package boiler. Came out of the factory looking like this and got hauled in on a truck. Any questions on chapter 3? Shall we dive right into electric boilers? How many of these are advantages of electric boilers? All of the above. Very efficient, compact, no fuel storage space, quickly and easily installed. So even easier than a package boiler because you don't even need a fuel supply other than wiring. Every boiler needs some kind of wiring, and no, not even a chimney or ductwork. Disadvantages, 2 things. And this is debatable, but this is what the books stress, the courses stress. Anything that's electric is expensive to run. That really depends. But this is what the textbook is telling us. And then limited to lower pressure. Energy cost is high and limited pressure. 2 designs of electric boilers, one called an electrode type. This is self-regulating and needs electrolytes for the system to work. And an immersion heater type. Immersion heater is much like the kettle you have in your kitchen. You put water in it, you want to boil some water to make drip coffee or tea. It's immersion type. Turn on the power and it boils the water, right? Electrode type is different than that. It has actual electrodes submerged in water. This one has a generating chamber. Water needs to have some electrolytes added so that it can conduct electricity, and then that electricity will basically directly produce steam inside the electrode type boiler. Immersion type looks much more like a standard boiler. Of course, you won't see any furnace or burners or coal-fired because this is electric powered. We simply put a heating element into the shell or drum, connect up some electricity. When we turn it on, it's going to make steam. When it gets up to control pressure, it will turn off the electricity. And as we need more steam or less, it will turn on and on. Some of the heating elements can be bundles, they can be multiples, and you can run it with 1 bundle or 2 bundles or 3 bundles or 6 elements and control it in that manner. Immersion heater, difference from electrode, water, the current does not travel through the water. It flows in the heating elements, which are submerged in the water. They look like that in most cases. Control is simply accomplished by turning on and off the power supply to 1 or 2 or more elements as required. Immersion heaters are arranged in the boiler. They're easily accessible for maintenance or replacement. So the one we saw here, the element is inserted here, has a flange on the end, and if there's a problem with it, you can take it out. Of course, you have to drain the boiler, isolate all the stuff. They are very efficient, but they are considered to be expensive to operate. Remember, 2 types, Electrode requires conductive water. We make it conductive by adding NaCl. Can you think of another way to say NaCl?
Salt.
Table salt?
Table salt, good. Or sodium chloride, same thing. Immersion type is different than the one that needs sodium chloride. Heating elements are submerged in the water, arranged so they can be removed and repaired or changed, and control simply by turning the power off and on. So in the electrode type, it's considered self-regulating. You don't even need to turn it off and on, because as the level around the electrodes decreases, the amount of current drops. So the more steam that's made, the current drops off. And then when level increases, it increases the current and makes more steam. So self-regulating or on-off control. Advantage electric boilers, high efficiency. Okay. Energy transfer to the water is close to 100%. Disadvantage, expensive. Cost of operation. Electrode type requires water that conducts electricity. Immersion type has groups of elements submerged in the water. Immersion boiler tube bundles can easily be removed for maintenance. To control the immersion heater, we simply turn on and off electric current to one or more elements. Electrode requires salt, sodium chloride. Electric boilers are very efficient. Disadvantage, cost of operation. Remember the two types and the differences. Immersion type. So this one shows where they've got 1, 2, 3, 4, 5, 6 really large bundles of immersion type heaters. Control the immersion type by simply turning power off and on. Any questions on chapter 4, electric boilers? Let's talk about fittings. Pressure equipment safety regulation defines fittings, and this definition will come under almost any code or regulation. It covers valves, gauges, regulating or controlling devices, flanges, pipe fittings, appurtenance, some sort of gizmo attached to or forms part of a boiler, a pressure vessel, a fired heater, pressure coil, thermal liquid heating system, or pressure piping system. So pretty much anything that's attached to or forms a boiler comes under the rules and regulations for fittings. Some of those fittings are pressure gauges. If you have a pressure gauge on a steam boiler, you must have a siphon. Pressure gauges, according to the textbook, are graduated in kPa. Many of you are going to know that that's not entirely true, but that's what the textbook says. Siphon is essential. Siphon is an essential fitting on a steam boiler and any pressure gauge or pressure control. Okay, hot steam into bellows and or board on tubes, not the best situation. Simply put in a siphon and creates a seal of water between the hot steam and that device. All boilers, any kind of boiler, will have a safety valve of some type. Any pressure vessel, any pressure piping will have safety valves. Safety valves on steam equipment have what's called a popping action due to steam acting on a disc lip. And we'll look at that a little closer when we get to those diagrams. Gauge glass. All boilers will have some way to know the water level. Gauge glass indicates level in the drum or shell with or without a water column. In many cases, we add a water column. There wouldn't be a water column and no gauge glass. There can be a gauge glass with no water column. Water column is added as extra equipment when there's a gauge glass. Water column allows us to have what's called tricox, so we can check the level if something goes wrong with our glass. Glass is fragile, it can break easily. If you have a water column, it also dampens fluctuations a little bit more than the gauge glass. Gauge glass is connected across what we call an interface between steam and water in the drum. And we can see water moving around in there. Similarly to the level in the boiler, it will be a little calmer, a little smoother. But if we add also water column in between, it's going to be leveled right down, evened out. And the added advantage, we can trap the sludge and sediment. So all boilers will have a gauge glass or similar device to tell us the water level. Sometimes the gauge glass will also have a column. Okay, if there's a column, there will also be a gauge glass. So here's the column between the boiler and the gauge glass. This one has 3 tricox. So since these books were written, the requirement for the tricox has been dropped from the codes. So you can see columns now without the tricox, but if they're there, that's what you can use them for. Check the level if that is right. The other thing about the column is it dampens water level fluctuations, traps sludge and sediment, lets you blow it down from time to time. Okay. All fittings, all these devices need to be marked. They need to be clearly marked with something that you can read. The 3 things, this applies to fittings, this applies to valves. Valves are fittings, okay? Manufacturer's name or trademark. Service designation means the pressure and temperature reading. And material designation means what is it made out of? Is it steel? Is it cast iron? Is it some other kind of material? Steam pressure gauge is a basic fitting on boilers. Each steam boiler must be equipped with a pressure gauge to indicate the pressure. Most common gauge we'll see is this type of board-on tube. Board-on tube is a C-shaped tube with an oval cross section. So when pressure increases in the oval cross section, it forces this tube to go straighten out, pulls on a lever and turns a gauge up and down the dial. Board-on tube expands and straightens as pressure increases. To move the pointer, remember that these are graduated in kPa. Siphon, an essential fitting between a steam boiler and the pressure. Not necessary on a hot water boiler. Boiler is already full of water. We don't worry about steam going into the gauge. Feature of This kind of a siphon, or commonly called a pigtail. Why is it called a pigtail? It looks like a pigtail. Is the inspector's test connection. A gauge can be connected here to a certain accuracy, or check the accuracy of your gauge. So there's a siphon, there's a siphon, there's two siphons, there's a control and a gauge on this boiler, so there's one siphon on each. Sometimes called a pipe siphon, and it maintains a water seal between the steam in the boiler and the board-on tube and the pressure gauge filled with water. So installing these, you can dip them in a bucket of water and make sure they have a water level. Really not necessary, because once steam is allowed to enter this, it cools down and condenses and fills itself with water anyway. So if you're installing it on a live hot boiler, you might be inclined to put it in a bucket of water. If you have a cold boiler shut down and you're installing the siphon, as you warm it up and fill it with steam, it's going to fill itself. Safety valves. Every boiler is designed to operate below, just marking down times here to see what we're doing. Below a specific maximum pressure. This will depend on the design of your boiler. Each design will have a maximum allowable working pressure. And no matter what that is, there will be safety valves installed to protect boilers and other vessels and piping from overpressure. If something were to go wrong, an instant loss of load, failure of valves and automatic valves are things that can happen to increase pressure and increase it suddenly. We want to prevent bursting the boiler drum, of course, or other pressure parts due to excessive pressure. So we have at least one pressure operated safety valve installed on each boiler. The normal safety valve looks like this. We have the valve part is in here. There's a disc sitting on a seat. Big spring on the top holds the disc down against the seat. Something called an easing or tri lever connected to the top. This is just simply a method of lifting the valve off its seat manually for checking it. We'll talk about that. Important that it's mounted on top of the steam space. So if our boiler drum is down here, we're going to put this guy on the top. It's going to sit upright because the steam pressure pushing against the disc inside as a function of the disc area creates a certain amount of force. So if we have 100 psi steam and 4 square inches of disc, we're creating a certain amount of force pushing against keeping the valve closed. So the spring on top needs to counteract that force and be greater than the force pushing it to open it up under normal operations. The steam in the boiler, steam pressure in the boiler comes up to, let's just say our normal operation is 100 psi. Our safety might be set at 110 psi, approximately. The pressure comes up over 100, gets approaching 110. The force from the bottom will overcome the force of the spring. And depending on the area of the disc, will create enough force to lift the disc off of the seat. Remember that the force created by steam is a function of the disc area. So if this disc area is bigger, there's going to be more force created. So think about that pressure coming up 105, 106, 107. if it's below set pressure or below that 110, it's acting on the exposed valve area, the disc, and not yet creating enough force to open the valve. Pressure of the steam continues to increase. Controls have malfunctioned, or steam turbine that's being operated is suddenly shut down, trips out. Pressure will increase rapidly. Once we pass that set pressure or go beyond equilibrium, the disc will start to lift off its seat. So this disc area that's being exposed is between here and here. When the disc rises or lifts off the seat, the area of the disc becomes this greater area because of the lip on the edge of the seat. So at that point where force from the bottom overcomes force from the top, it lifts the disc, and then immediately the surface area of the disc is doubled. So now the force is doubled instantly. This is called a pop valve. It's going to fly wide open. Increased force, increased pressure, increased area, doubles the force, lifts the valve wide open. Escaping steam strikes a lip around the disc, increasing the area of the disc approximately double, subject to the steam pressure. And that causes the valve to open. Sudden increase in area under pressure makes the force much more imbalanced, makes the valve pop wide open. Escaping steam striking the lip increases the area of the disc subject to the steam pressure. Any questions on how that makes that valve pop open? Fairly straightforward, I think. Lift testing. So I talked about a safety having a tri-lever. And we have started up a boiler when we're getting our equipment warmed up. We might want to do something called a tri-lever test. Having a safety that's in operation and completely functional is absolutely imperative to boiler safety. When we have a tri-lever, we can operate the tri-lever and check that this safety is free to move, that it's not stuck. Safeties can get stuck, they can get, the discharge piping can get frozen. Sometimes these safeties are near the roof of the boiler room and the discharge pipe is kind of leaky and cold air is coming in, and even though there's a drip hole in the pipe, there can be some steamy condensation, freeze things up. Scaling inside the safety can cause some sticking of the valve. We need to know that we can check this thing. It's a tri-lever test. We simply operate the test lever for 5 to 10 seconds. On low pressure boilers, tests should not be performed unless pressure is a minimum value, right? If the valve continues to leak or pass, or what we call simmering, we can try it again. So we've tested it by operating test lever, allows steam to escape 5 to 10 seconds. If we can't operate that lever and we find the safety valve stuck or closed, can't open it, we're going to, at that point, we're going to shut down the boiler and have that safety valve removed and checked or repaired. An actual pop test is a different kind of test. Tri-lever tests you can do as often as you like. Sometimes boilers that run continuously for long periods, you do that weekly. It might even be a monthly test. Pop test is a test done when you just want to make sure your safety, and this might be a weekly or monthly test. But we actually raise the pressure in the boiler carefully You can isolate the steam discharge or raise pressure beyond the control by whatever means you want to do. Do it slowly, do it carefully. If your setting is 103 kPa, we should see that safety valve open within 2 psi of or 14 kPa of the setting. When the safety does pop, you need to shut down the burner and observe and record the pressure. If the valve sticks or is stuck or doesn't pop or doesn't reseat, you need to shut down and replace or repair. Before a pop test, ensure the pressure gauge is indicating. So if you have that inspector's connection on your main steam gauge, you can put a second gauge on. Maintenance guys will have a calibrated electronic gauges now. They carry it around in their tool pouch with different ranges on it. You can set it up for your boiler and check out your gauge. Conduct a pop test by slowly increasing boiler pressure until the safety actually opens. Note the pressure when the valve opens, and you might want to pay attention to what the pressure is when it drops down and closes. The seal is on the adjustment nut, so let's go back. Seals, safety valves should not be adjusted or tampered with by anyone that isn't specifically trained. So there's adjustment under a cap for increasing pressure on the spring, but never done by operations personnel. So once it's been adjusted and certified by the valve shop, the trained authorized people, they will put a seal on to prevent any midnight adjustments to the settings. Okay. Adjustments are only done by qualified individuals, and that comes out of a boiler code. Directly connected gauge glasses. So we looked at some gauge glasses and water columns before. So here's a gauge glass directly on the shell of a fire. I guess this would be a firebox boiler, but gauge glass should be located to ensure we always have enough water above the lowest permissible water level. So there's a marking on the shell that says never go below this level. Okay, this is the lowest that you can ever go, that you won't probably have severe damage because heating surface is not cooled by the right level of water. It's going to overheat and probably burst if everything's under pressure. So the very bottom of the gauge glass will be at least an inch above that minimum water level. So if you see the water level disappear from your gauge glass, you've gone too far, shut the boiler down. Okay, your low water fuel cutoff should have already shut this boiler down, but if there's some fault or buildup of material in there because you haven't been correctly blowing it down on a regular basis, you could go lower. If you've gone this low, it's too low, shut it down. If you see the water go below the glass and you think, oh, I'm going to pump a bunch of water in there in a hurry, this is a good way to have a disaster. All right. Gauge glass breaks, close the valves. First action, case of a broken glass, close the valves. So we looked at a gauge glass directly attached. Here's a gauge glass with a water column. Okay, this gauge glass should still be lined up a minimum of an inch above the lowest permissible level in the boiler. Water column allows us to have more options for connection of the water gauge glass. If we have a low pressure, so this is connected down here and up here, more options. If we had this particular gauge glass, we'd have to be connected in a different part. All right. Generally made of cast iron for lower pressure boiler. Dampens the water level fluctuations, traps sludge and sediment. May have the tricox. Code in the past said they must have the tricox, but we changed this to may because current code does not require them. In the book, there's some guidelines replacing gauge glass. While you're replacing it, you can continue to run. Just make sure you can check the level. Most boilers will have level indication instrumentation in addition to the gauge glass. So you can see a trend on that and double check with these small drains on the column. Then you can spend some time getting a new gauge glass installed without too much trouble. Some other boiler fittings, stop valves. Remember their types. There's globe valves, there's gate valves. Some things to remember about them that we'll look at in chapter 17-ish, I think. On Tuesday, check valves only allow flow in one direction and not the other direction, okay? Lift check valve is different than a swing check valve. What do we check with one of these, three of these? Water level. Steam pressure gauges are graduated in what?
Kilopascal.
Yeah, kPa. Very rarely will someone use this language. It's going to be kPa. Essential fitting between a boiler and a steam pressure gauge.
Siphon.
Siphon. It can be spelled SY. It can be called a pigtail. What does it do?
Prevents water or steam getting up the end.
No, not this one. This one.
Water.
Careful. Careful with that. That is picked 60% of the time. Keeps the steam out. It fills with water. Okay. It might look like this. Doesn't have to be a pigtail. Okay. What does this test connection let us do?
Test the gauge, see if it's operating proper.
Yeah, install a test gauge. Blow down of a safety valve. Remember I said if you're doing a pop test, make a note, where does it pop, and then be careful and monitor when it closes. So that's going to be two pressures, one higher and one lower. So that's the difference between opening and closing. So if we're talking about blowdown of a boiler, it's blowing down some water from the bottom. If we talk about blowing down a level column, we're blowing down some water out of the level column. If we're talking about blowdown of a safety valve, we're talking about the difference between opening pressure and closing pressure. Okay, so blow down, blow off. Make sure it's clear which one we're talking about. How do we prevent tampering with a safety valve?
Seal.
The seal, correct. Okay. to increase safety valve opening pressure. So if we had our valve shop come and adjust this, how would they increase the pressure that it opens at?
They'll tighten the spring down.
Yeah, increase the spring compression. So more force going down means a higher popping pressure. Increase the spring compression to increase the set pressure. It can be called popping pressure. It can be called set pressure. And this one will really throw something into your brain. It's sometimes called, anyone want to guess? Not blow down, but blow off. The blow off pressure of a safety. That's the popping pressure. Blow off is the pressure at which it opens. Blow down is the pressure difference between opening and closing. Force of steam pressure on the safety valve disc is a function of what?
Disc area.
Yes. The lip on the safety valve does what?
Popping action.
Yeah, causes the popping action. If a safety valve leaks after a lever test, what are you going to do?
Try it a couple times after, see for receipts.
Yeah. To check boiler safety valve set pressure or popping pressure, slowly increase, check your gauges, get somebody to help you, slowly increase the pressure until the valve opens, note the pressure. When it pops or opens, also pay attention, note the pressure. When it closes, the difference is the blowdown. If a safety valve is stuck,
Shut down the boiler.
Shut down and replace.
yes, sirree. 50, water steam leaking if a gauge glass breaks. One of these.
Global valve. Safety shut plug.
Okay, these have little stainless steel balls in here. Should the flow out to the Mueller, I'm muting you again. Prevents water steam leaking if the gauge glass breaks. Safety shut-off valve. Cast iron is material used for which of these things?
Water column.
Yeah, water column. Okay, on a low pressure system. What dampens water level and traps sludge?
Tricox.
Water column. What is this for? Check the level.
Okay.
Okay, if this breaks, you can check the level with this. Gauge glass breaks, what are you going to do?
Number 4, the isolating valves.
Close the valves. Isolate, block in, shut off. Yep. Okay, boiler gauge classes may break because they erosive action of the steam can thin them. They are brittle, they break easy, and then if they get thinner and thinner, they're going to possibly break. Shape of a board-on tube, important thing to remember. It's not just a C section, but the section is oval. Letter C shape and oval in cross section. Okay. Somebody needs to be muted. Please don't go to sleep. Gauge class safety shutoff has the stainless steel ball. That's called a safety shutoff. Hydro tests. 1.5 times maximum working pressure. I think we're still in chapter 5, right? But we're close. We're close to the end. Purpose of the gauge class or water gauge.
Check levels in the, monitor the levels in the tank.
Yeah, always know your level. Level, all different kinds, right? Okay, that was chapter 5. How's everybody doing? Everybody's good. Everybody's happy. See some thumbs up. Cool. That's some of the chapters are going to be shorter. So, okay. Hot water boilers. So fittings on hot water boiler are much the same. Most of them are the same. Just a couple of differences. So these are going to go pretty fast because it's the same thing over again. A few things we'll dwell on if there's differences to steam or hot water. So when we have a pressure gauge on a hot water boiler, we'll usually call it an altitude gauge. We'll talk about why. Thermometer is required on a hot water boiler. You won't often see temperature on a steam boiler. Certainly there will be temperature being monitored, but you're not going to walk out there and worry about it. If your pressures are right, everything is going to be in the ballpark. We also have safety relief valves. We sometimes call them pressure relief valves on hot water boilers. They're not, they look exactly the same. They work similarly, but they don't have the popping action. Steam is compressible. When the pressure is too high, we need to get rid of the pressure immediately. Because water is not compressible, when that relief opens, the pressure is basically zilch immediately. Okay, there's no reason to exhaust what's in the boiler. Safety pops, pressure is dropped down. Steam boilers will often supply steam to a system without any isolation valves. When you shut down a steam boiler to drain it, you want the whole system to be drained. You don't keep your lines full of water. If you're shutting down a hot water system, you might want to keep the water in your system and just drain the boiler. So they have stop valves, shut off valves, isolation. Something you won't see on a steam boiler is an expansion tank. And there's a couple types we'll talk about quite a bit. One type we'll only mention briefly because they're not really in use anymore, except in very old systems. So the pressure gauge on a hot water boiler will often look like this. It will have a movable pointer, which means we can indicate the pressure that we need to have for good performance in our hot water system. So we move the pointer a little bit above the height of the system. You'll see a distance scale on this gauge. And then we know when our operating pressure is at least that amount of pressure, we have the pressure that we need to effectively supply our whole system. Pressure gauge or altitude gauge on a hot water boiler, no siphon is required. Things are full of water, no need for a siphon. Thermometer, linear type or old school. or temperature gauge, sometimes in centigrade, sometimes in Fahrenheit. Safety relief valves installed on the boilers are close to the outlet, so at least one safety rated relief valve. Isolation shutoff valves may be installed on, shall be installed on supply and return so that we can drain the boiler only and keep the system full of water. So what's different on this hot water boiler is the expansion tank is called a compression tank. Just be aware that that's a word that covers the expansion tanks we're going to look at. Expansion tanks. So there's an open type, a closed type, and a diaphragm type, sometimes called compression tank, sometimes called cushion tank. Normally it's going to be attached on the supply line or the outlet. Hot water from the boiler is where we're going to attach the expansion tank. This is called a closed type expansion tank. And we'll look a little closer at the different types. Relief valve is still close to the boiler outlet, so relief valve on a hot water boiler. No siphon between the gauge and the boiler. Thermometers or temperature gauges. Combination gauge. So I showed you altitude gauge earlier that has the additional pointer here on the pressure side. This one is combination in that it also has a temperature gauge built into the same gauge. Check the pressure and temperature on one gauge. So back in the day, we had a big tank up